Okay, hi everybody. We are live with Stephen. Satoshina is taking is sleeping right now. He's the mascot of our show, uh, Satoshina the cat. The show is me, Stephen, and Satoshina the cat. But anyway, so let me see if I can find a better way of because there are all these overlays. Let's try this one. Okay, I think it is better. All right. So this is episode number 4 of Bitcoin, and so the physics of Bitcoin. This show is called, and we cover different topics that are somehow related to physics, and we have a different view that maybe other people that analyze the Bitcoin price action or topic related to Bitcoin. And so we try to bring our physics experience and expertise. So the first thing today, we are going to talk a little bit about the market. I have this trading view indicator that I develop. One of the recurrent themes in our meetings here is the idea of a power law. So we use the power law as our say current best model that allows us to understand what happens with Bitcoin. And I think most people are familiar, but basically the idea is that Bitcoin price follows a power law. A power law is basically a simple relationship where you have Y, in this case is the price, versus another quantity, in this case is the time, and there is a power. So it's going to be price equal time, and it's a number that is not quite 6, but it's very close to 6. And there are reasons, we think that has to do with the hash rate, with the addresses, with how the addresses grow, and addresses are supposed to be a proxy for adoption, right? So ultimately, adoption is really the key ingredient that makes the price go up, and the relationship between the addresses and the price is also a power law, and is very, very close to basically what is called the Metcalfe law. And Metcalfe law says that if you have a network, because the idea that also links this power law with physics, because we study one of the topics that we study in physics is networks. One of the most famous network scholars, his name is Barabasi, and he's a physicist, and he studied the property of network. So the value of a network, according to Metcalfe law, it's the square of a number of nodes. And so if you're thinking that addresses are somehow the nodes, because they are supposed to represent centers of activity, right? So it doesn't have to be a single individual. It can be a company, it can be an organization that is managing these addresses, and then it becomes like a center of a network activity. And so you call that center a node. And Metcalfe says that it's a derivation that you can, it's a relatively easy derivation, which says at the limit that really the square is valid with this simple result is valid when the number of nodes is very, very large. It's kind of a limiting value. When the number of nodes is very large, when the value, in this case, the price of a network is proportional to the square of a number of nodes. And this is exactly what we observe with Bitcoin. It's not exactly 2, it's like more 1.75, something like that. But you can think about like a generalization. It doesn't have to be the same value, because the result from Metcalfe is kind of an ideal result. It's like a theoretical result. And so it's actually okay that it's not exactly 2. It can be close. And this is the picture that we have right now, that basically there are this cycle, there is the general trend for the power law, and the cycle structure is um, very periodic. That is another thing that it's familiar and fascinating for physicists, because one of the things that they teach us in physics is how to understand, we develop this language and these tools to understand periodicity. It's one of the things that we look in nature. Like when things are periodic, it's actually quite useful, because their periodicity are predictive. Because if something follows a certain periodic pattern, then you can predict when the next thing is going to happen. Right? That is one of the first achievements that we got in physics when we started to understand the motion of the planets. Right? You could predict when the next eclipse happened, and other things like that. They were kind of mysterious things for the ancient people. They did have some astronomy that somehow could predict the eclipses, but not as precisely as modern science did, right? And so it's very fascinating for physicists like me and Stephen to think that we are dealing with a system that, for some reason, and part of what I'm going to discuss will be the second part after Stephen does his presentation, why we think it's true, not just true because of the data, but also the foundations, right? Maybe the theoretical ideas behind why is so regular, almost like if it was some kind of a natural phenomenon. So the power law is something that we find often in nature. That is the first link, and the second is a very precise periodicity that happens every 4 years. It's also something that we find in nature. So Bitcoin basically has both characteristics. It's has this general trend, and then this very precise periodicity that are the cycle. And I don't know, Stephen, maybe you can tell me how you think about this, but my approach so far is very empirical, in the sense, many people say the cycle is going to break because there are all these big events like the ETFs and Sailor and maybe the strategic reserve. My position about that is, well, until I see evidence that the cycle is not behaving like in the past, I'm sticking with the cycles, because this is what the data tell us. All right, it's not a lot of data. We don't have a lot of cycle. We don't have hundreds of cycles. We only have 3, but it's all what we have. And so far, it will be unscientific to say, oh, it's going to do something else, because basically you go from data to basically hand waving, and making speculations. And I'd rather stick with the data. Now, when the data tell us, okay, we don't have another cycle, you see here in the model, I made this, what is called the full model. I'm including the periodicity, including when the next cycle is supposed to be, if it's regular like before. The cycle is supposed to have a top in November of next year, and we calculated what we think the top is based on also another data, the fact that the decay of a top is also following a predictable pattern, right? We will have to see if that component holds, because to be honest, is the weakest component of this discussion. But if there is a decay of a top, then we can even calculate what is that value, and it's supposed to be 200,000. But this is the picture. I can go a little bit more in the indicators, but I want Steve to present. One more thing I can show you is I have this other indicator here. Basically, what it does, it compares the 3 cycles together. Basically, all what I did here, it's almost like a map of a territory. What I did here is to superimpose the different cycles. The way I achieved this was, I go here to whatever date we have today, and then I basically go back 4 years. So whatever you see here is whatever place we had 4 years ago, right? Relatively to whatever date you're looking. So today, this will be, if we zoom in and we look at the previous cycle, this is how it looked 4 years ago. So it's a kind of nice way to compare what we are doing today with what we are doing 4 years ago. And to me, for example, it doesn't look anything different or anything like you will expect, because of all the FOMO created by the strategic reserve, or because of the ETF. We are moving fast up, much faster than in previous cycles, but we don't. We are doing exactly what we did last time. The bull market started about November. I draw this line to indicate, basically, it's kind of a demarcation line. Usually the bull runs happen at the end of the year. The first one actually happened just a little bit after the end of the year. These two seem to have happened more or less at the same time. And the idea that we are in a bull run is because most of the time, this is the overall picture that I have in my mind of how Bitcoin behave. Basically, we have 1 year where we go up in almost in exponential fashion. We go down in a also exponential fashion, and also these last about 1 year. This is very, very, very similar. These are the things that, as a physicist, you will try to understand. Are these cycles regular, right? They look almost like copy of each other, right? When you compare them like this. And then in the next 2 years, basically we move along the bottom of the power law, is what we call the support power law. And most of the data is actually between the trend, the middle trend, and the bottom. Almost all of it. Sometimes it goes a little bit above. Here we just touched, and then we had a correction. And so most of the time we are in this region, and we follow the power law. But the general result, even if we go up and down, is that basically the bubble cancel each other, and you still have. It's almost like they didn't exist. You can draw a line, and then from here to there, and you will see it follows the power law. It's like basically almost like the bubbles disappeared, and here I'm showing even more directly, because basically I'm taking the deviations from the trend, and I normalize them, because the first bubble was enormous, like was about almost 11 times bigger deviation relatively to the trend, the power law trend. And last time we had like about 2 times the deviation from the trend. And the projected one this time is about 80%. This if everything goes according to the theoretical calculations. And here you see I superimpose them, but I normalize them by the price. When you normalize by the price, the peaks seem to be kind of similar. It's a very good normalization to have similar peaks, so you can compare them. And same thing with the bottoms, right? You have they all tend to kind of bottom at the same place. And that this is like this line here will be the power law. And you see during the bubble we are above the power law, and during this period here we are below the power law most of the time. And here you can have a zoom in. So the bubble didn't start, the bull run didn't start for the first cycle yet. It will start after the end of the year. But the previous cycle here is in yellow, and the current one is white. And you can see they almost superimpose until now. And then what is different is that you have this spike. We basically started to go up very, very quickly last cycle. We can go here and see what happens next. The movie spoiler, spoiler alert. Like we are trying in this way. You don't know what happens next, but you can always go back and see what happened. You see this what happens. It happens this where we went up very, 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 very quickly. It lasted about a month, and then we had a correction. So it's possible actually that this time we kind of repeat this where maybe we have a double top, right? It's not unlikely that we have something like that. It looks like for some reason, whatever, maybe it was COVID, and the stimuli that we were, all the different financial stimuli that were given, and people invested in Bitcoin, and so it pushed the price very fast up, and then it corrected, and then for some reason, maybe because synchronization with some macroeconomic event, we still had another top later where it was supposed to be, and then finally we had the bear market. So this kind of a review where we are now, maybe we can do small review and updates on a regular basis like this, and according to this view. Do you have anything to add or comment on all this, Stephen?
A little bit of a comment plus a question. We see that Bitcoin skews right. It spends most of its time between -1 standard deviation and +2 standard deviations, right? So the peaks take us up to around +2 standard deviations, or z-scores near 2. Is that where you are with your projection at 200,000? Does that roughly correspond to a z-score?
It corresponds to I didn't transform it in a z-score, and maybe if you have some calculation next time, we can show your way of doing that. My main way of doing this, it's relatively simple, and I can show you basically the main idea behind it. And it's interesting because you can do it 2 or 3 different ways, like the one that you suggested. So I have this indicator where basically I took away the decay, the exponential decay, and then you can see they are almost perfectly normalized, and you can actually use it to almost pinpoint where the peaks are, where the bottoms are. But so these are different way of calculating the deviations. So I have one where I do it relatively to the trend. Okay, so if you do it relatively to the trend, so basically it will be a calculation where you have price minus the trend. In this case, the trend means this line in between, in the center, right? That is the general power law trend. So you take the price, you subtract the trend, and then you divide by the trend. So what we call the fair value based on the power law, right? And then you multiply by 100, and you get these peaks, and you can see how the peaks are going down quite fast, right? This was the first bubble, actually the one that happened before the halving. I'm mostly modeling the one after the halving, but if you include this one, this one was almost like 15 times away from the middle, right? This one was 11, this was like 5. You can actually check it here where I look at where the peak is, right? 500%. This was 1,100%, and so on. The last one, if you use this one, was more like 195, so like basically 2 times. The cool thing, and this shows you our right to the calculation of the top, if you take the logarithmic version of these deviations, you zoom in and you look at the tops, something happens. And I was always surprised by this thing, because now all the peak, right, within, of course, there is always a little bit of error. And when we do this, it's not just drawing a line by hand, you'll use regression, etc. But you can calculate the deviation in terms of the so you can do it from the bottom, you can do it from the this linear, this central line, the power law line. If you do it, in this case, it's done using the central one, and so all the deviations are expressed in that way. Then it looks like there is a very precise pattern on how they decay. And we say so many times that if you draw a line in a what is called log linear, where you take the log of a y-axis and is linear in the x-axis, it's an exponential, right? So basically this means if there is a straight line through these points, and it's so cool, and you will expect a decay, maybe, but why so regular? That is one of the mystery that I don't know, because it's one of these places where I will expect more disorganized behavior. And actually, Stephen, you have an idea about that, right? You explained me a few times. It's almost like a diffusion type of situation, and maybe you can explain that. But it's another regularity we observe in Bitcoin, and the idea is, well, see here is these deviations. They are color coded, where as they become bigger and bigger, they start to go bigger, and basically, because we are doing it relatively to a center, when you do the log, you have these regions where this is below the power law, this is above the power law. It's almost like a bimodal pattern that you observe, and we are, this is another indication we are in the bull run, because we are kind of above the power law in a very decisive manner. But the idea will be this line will continue to grow, right? These deviations will continue to grow, and then basically by the time we have a end of a next year, that is kind of here, right? We can even draw it with a line. So I can draw a line there, like here. Okay, this line will meet the decay line, and we can read from the chart. I mean, again, I did all these using rigorous calculations on, but even visually, kind of rough method to estimate this value, it's about close to 80%. We get an 80% deviation. And if you look at the value of a power law during that time, so if you go back and you say, okay, what was the trend value? We're talking about something close to 130. So basically, we are expecting an 80% deviation, added to 130. So basically, you get 200,000. This is how we did it. This is how we arrived to this value. But you can disagree. You can say, well, not necessarily we will continue to follow this decay, but it's really the only thing we have, because, and maybe it can be done in other ways, etc. But it's really the most mathematical way of calculating a possible, right? It's just an hypothesis. Say, look, if this decay continues and it works in this way, then this is what to expect, right? So it has to be taken with a grain of salt, because differently from the power law that has literally thousands of points, we are talking about 4 points, and so the stats are not very, very strong. But it's really surprising that there is this decay. So maybe it's meaningful. Maybe there is a reason. Do you have any feedback about this?
My view is that the decay is directly expected from the power law nature of the overall trend, and that means that volatility is dropping. And even before you look at the power law behavior, if you just look at the data, you see very clearly that both return and volatility are dropping from one epoch to the next. That's completely consistent with the power law. If you model it only with the power law prediction for the decay and the volatility, you underestimate the actual observed volatility. And so I've suggested that that could be due to basically the influence of these, exponential peaks and falls, and that they diffuse some additional volatility into the whole process, kind of like a diffusion process. And empirically, it fits a diffusion model.
Can you explain the idea of a diffusion model? What do you mean with that? To the audience.
Well, in kinetic theory, you just have transport and diffusion. So you may have a bulk velocity where you're transporting in some direction, but you've got a thermal component as well. And that's going to cause some general diffusion as well. And it's a combination of those two. So they both have some grounding in physics.
Exactly. And you were saying returns. So you see, for example, this is a picture of the returns. So what I'm doing here, I'm taking the daily returns average over 1 year. And if you do that, right, you get another pattern that is very clear. Basically, by the way, the blue line is the theoretical value. That is basically this formula. I use anno, that in Italian is year, because I was explaining this to an Italian audience. But anno is year, and you are super familiar with that formula, right? You calculated yourself many times. But basically, if you want to know what is the yearly return, you take the number of years from the Genesis birth, the Genesis block. You're adding one. You divide by 16, and then you take the power of this power law, in this case 5.7, and what you get is 1.41, which basically means right now we are doing about 41% a year. And so this, you can use this, but you also can do it with days, right? You can put days, and then it will tell you what is the average return per day. Right now, for example, if you do that calculation, we are doing about 0.1% a day, and this is what you get here. See, if I go there, I get 1.01. That is 1.020 that if you calculate the compounded value of that over 1 year is about 40%, 41%. But and this is what you see. The power law is not just like a line that we draw arbitrarily. It's actually a statistical property of a system, because you see returns, in a way, returns should almost eliminate any trend, right? But the trend is so powerful there that even the returns still show a decay. What we call it the diminishing returns, right? These are you seeing here the diminishing return, and it's not just the peak that are. This is why you are right. I think you are deeply right. That is not just how the peak decay, because one could think, oh, it's something that has only to do with the peak. The overall returns, all the returns are decreasing, including the peak. So it's very intimate relationship between the decay that we observe with the power law, because it's basically a result of the power law nature of Bitcoin, that you are going to have diminishing return. And you can see what the bubble simply do, it's like a general oscillation around this general trend. The blue line is basically this formula, applied to days instead of years, but it shows that we had very strong returns early on, and then we are going down, and this basically we are kind of flattening. We are basically going towards one, right? We will never reach one. One means nothing. It doesn't go up or down, right? And we are going slowly towards that one result. But basically, for the next 20 years, we are still going to do more than 20% a year, according to the power law. And the idea that you could also use this as another way of calculating the next, because I could do this. I could take the logarithm, and then again there will be some kind of exponential decay there of these peaks using returns, and then you can extrapolate and say, okay, how big the returns will be here at the end of the year, next year, and then you can use that to calculate how big the top is, and you get a very similar result, very close result. I think like Stephen was saying, you are using the other method, you are underestimating. This one gives us more close to 250 when you do it in this way by using returns. So it's kind of cool that by using two different methods that are somehow similar but non-identical, you get very similar result. That is kind of cool. Okay. So now I'm going to take some questions, see if there are some. You can ask question about what we are showing right now. and I'm waiting for Stephen to come back because he's going to tell us more about.
Okay.
Yeah. So I was telling them you can use the same thing here with you can fit the decay of these tops, and then you will get something closer. And you're right. When I do it with the returns, I get more like 250. When you did it, did you get a value similar to that?
Yes. Right now, if I run a generalized least square, it has a slightly higher power law index, a slightly higher fair value of around 90,000 now. If you project that, forward half a year, it's going to be 20% higher in the fair value, which puts you on trend at 110, mid-year in 2025. And using my transport plus diffusion modeling for volatility, and based on historical volatility, I expect volatility in the logarithm to be 0.21. That's a multiplicative factor of 1.6. And if you go to 2 sigma, then that would be the square of that, which would be 2.5, 2.56.
Right.
And if you multiply that on 110, even by the middle of next year, if the peak happens then, you'd be above 250K if you got to 2 sigma. But that's something you can come near to and maybe touch or not. So in general, this idea of somewhere between over 200, most likely up to about 250. And, if the peak comes a little later, then it can be higher, right? Because you're getting 10% every quarter,
right,
just off of the trend.
Yeah. So, and this to me is good because I don't want to push my hopes up, right? Like, we're going a million, etc. I think it's quite unlikely, and I'd rather focus on something that is quite achievable. All the numbers seems to point in that direction, and then maybe be surprised that we go 300, 350, then the other way around, where I'm hoping for this completely unrealistic results, and then it never happens. So that is my approach to these kind of things. Anyway, Stephen, do you want to start to talk about quantum computers?
Yes. Enough about classical
Right.
physics.
Let's go
talk
to
about
quantum physics. And I'm going to stop my presentation, and I'm going to you can start to post yours. I'm going to activate it. Okay, it is here.
That didn't work. Let's see. Try again. Window. Let's do. Here's what we want.
Okay, let me activate.
Okay, and then
perfect.
Let's go full screen on that.
You want to go full screen? Okay.
How is that?
Looks good.
Great. Okay, so let's talk about the quantum threat to Bitcoin. There's been a whole bunch of, flurry of interest and concern and worry, and it all came because Google announced their Willow chip, and we'll talk a little bit about what that chip is and why it's of importance. But really what we want to do is get the broader context of what the threats are from quantum computing to Bitcoin, and there are 2 main categories. And then we want to talk about, the rate of progress in quantum computing, and then what are the solutions? What's the mitigation against these potential threats? And both quantum computing and nanotechnology, in some sense, have their roots with a talk that Richard Feynman gave in 1959. He's my fraternity brother, but I never met him. His picture was on the wall. He used to go buy it every day. Of course, we used his books to some extent in our physics class, his supplementary text. I'm a partner at OrionX.net, and we're a Silicon Valley-based consulting firm. And I show this because we all come from a supercomputing and high-performance computing background. We were at Cray and SGI and Sun and other companies in the HPC space over the decades from the mid 80s through the 90s and aughts. So I'm not a quantum expert, but we've been tracking this from the vantage point of interest from the supercomputing, high performance computing side for 2 decades now. And this shows a bunch of our clients. And we have done some technical marketing work in the quantum computing space for clients as well. So here's the agenda. I want to first give a little bit of context with high performance computing and supercomputing, because that's really where quantum computing is seeking to play a role as one of the solutions in that broader space, as well as in cryptography, which has always had a historical tie to supercomputing. In fact, the second Cray system ordered went to the National Security Agency, and there were special features in the hardware that were designed to support their applications. And then why quantum computing? You know, what can it do potentially for computing in general? The state of the art, the rate of progress, the problem for Bitcoin and finance in general, the quantum algorithms of relevance, there are 2 main ones, and then solutions and resources. And if you have comments or questions along the way, Giovanni, please jump in. This is kind of a positioning with respect to the high performance computing market. Historically, that was very early on, single CPUs as fast as possible, you know, big monolithic mainframes, but at the high end of that. But then in the 1970s, vector capabilities were added as acceleration to the processing with the Cray and with others. And then over time, people added matrix coprocessors, and they did that in kind of custom silicon with FPGA and ASIC technology. But by now, we're in the era where supercomputers are built of very, very large computational clusters that have a CPU component, and very often they have a GPU from NVIDIA or one of the other vendors. And those GPUs are there to solve matrix equations and to solve tensor equations, which are higher dimensionality matrices. And on the left side, it shows a bunch of the different grand challenge applications that we have in HPC, everything from climate modeling through astrophysics and condensed matter and materials, et cetera. There is this term called quantum advantage that the quantum computing community likes to use. They're not talking so much about quantum supremacy right now, because really they have not been able to achieve it except for some very specialized toy problems. But they're looking for disciplines and algorithms and performance from their machines where they can provide some advantage in conjunction with classical computers. So the idea is that the quantum processor is a coprocessor or adjunct to the very large classical supercomputer design. And the expected quantum advantage application areas certainly are in quantum chemistry and physics, and that's kind of what Feynman talked about more than half a century ago, the ability that you can simulate nature, which is quantum at its basis. You could simulate that with the quantum machine. And then optimization, which is searching very high dimensionality spaces, and that's related to search in general. QML is quantum machine learning or AI. Quantum may be able to help in the AI domains. And then, of course, what we're mostly concerned about right now is cybersecurity. So why quantum computing? If you can build a quantum computer, there's the promise of much higher scalability. If you could build one that has enough of these qubits and that you can make it scale, and particularly you can make it scale in space and time and get the error rate down enough. So what is a qubit? It's a mix of quantum states. In classical computers, it's just a switch. The bit is 0 or it's 1, and that's it. And we just string a bunch of those together, and we use those for data, and we use those for our control code. And that's what a von Neumann machine is, you know, a stored program logic with a bunch of bits lined up. What a qubit is represented by this sphere, block sphere, and that's not a solid sphere. We're just interested in the surface of that. and it has the 2 qubit states shown at the poles. And by convention, at the North Pole, they put the 0 value, and at the South Pole, they put the 1 value. I'm not even sure why that's the convention. But the qubit can be anywhere on that sphere. It's a mixed state. It's not a pure state of 0 or 1. So it's a mixed state anywhere on that sphere. And the location on that sphere is given by 2 angles, this theta and this phi. The theta being the angle with respect to the pole, and the phi being an angle in a plane. And then there's an expression below, and that basically gives a wave function, which is a probability function that applies for that qubit.
So just a second, Stephen. This is the theory behind, right, where we can represent the state using this quantum superposition. But in practice, what they will do to achieve this, right? Because this is a theory of a abstraction, but if one had to understand concretely, how will you do this?
So that's where I'm headed right now.
Okay.
So you need more than one of these. You need a bunch of them working in concert. And what you need is this wave function that is written down. You don't have to worry about the details, but you need those to be superimposed or entangled across multiple of these qubits. And these are logical qubits, and we'll make the distinction. So if you do that, and you have small n qubits, the state space for the collective grows as 2 to the power of n. It grows exponentially fast, as opposed to classical computing, where it grows as 2 times n, and those n's are not necessarily the same number. Those could be different numbers. But because 2 to the n power is an exponential, there's going to be some moderate n for which the exponential state space is much larger than your classical machine, even though you have many, many bits in the classical machine. So if you can find a problem or algorithm that can be coded for a quantum computer, then in principle, it can be much, much faster. And, it might be faster by 2 to a high power, for example, assuming all other things are equal, which would include clock speed, and I'll get to that. So rotations on this surface of this block sphere represent quantum gate logic, but you have to have multiple together, and then you can build a quantum gate. And it might have 2 or 3, depending on the details of the particular quantum gate.
So let me interrupt you here.
Yes.
I know all this stuff, but at the same time, your presentation is so good, and I want to kind of ask questions, almost like if the public was going to ask. So you are saying I will need a certain number of bits to solve a classical problem. That number is n, let's say. But you say, well, you could have the same information, the same information space, but with much less of these qubits, because you could find a number n with a small n that it's less than, basically you will have 2 to the n that is close to that n, but then n, because you are taking 2 to the n, will be smaller than big N. Is this what you're saying, right?
Well, yes, and to add to that, you're searching in a much richer space. So this is by nature inherently parallel, whereas classical computers are inherently sequential, right?
So that is
follow, do this,
then
do the next step, then do the next, right? Whereas here, you do your computation in parallel across all the qubits at the same time.
Yeah, that is the other advantage. You can not just a small n is less by necessity, because 2 to the n is actually your space. That is going to be a big number that could be kind of close to n or even bigger than n. But by necessity, n is smaller, but at the same time, you're solving all these problems, all these section or subsection of a problem in parallel at the same time. And that is maybe the biggest advantage in doing this with quantum computers, right?
Right. I mean, it's the fact that you're doing it in parallel that allows you to say that the speed goes as 2 raised to some power. So what the process is, you entangle many of these qubits together, and then the computation proceeds on the system in parallel, and hopefully all the qubits remain entangled, connected in quantum space with their wave functions superposed, overlapping, right, and influencing each other. And then at some point, when you think the system is settled into kind of an ultimate, more or less stable state, then you do a readout, and that's supposed to give you your answer. So the analogy that I just thought of this morning, but it's a pretty nice one, is this kids game freeze, where the kids all dance around, and then the teacher, the instructor, tells them to freeze, and then they're all in different positions, but that's your final state, that's your readout, that's your answer. Now we want to add one element to this, which is the coupling. And that coupling might happen because the teacher has given directions for a choreography to tell them to move in a certain way. Or even very simply, as an analogy, you could just say, okay, every kid has to hold the hand of the kid next to them and the kid on the other side, right? And then they're all physically coupled. They all move around. You don't know what configuration they're going to end up in. And then at some point it freezes, you do a readout, and you don't even know how they got to the final state, but you get a final state.
The entanglement, in a practical term, is achieved by creating some kind of a state, right, where these two particles are somehow connected. And in quantum mechanics, so let's say, for example, you create two particles, right, from whatever, and then the idea is that if you started with 0 spin, let's say, by necessity, so you started with a particle that had a 0 spin, is one of the quantum mechanical properties, not necessarily what we think when something spin, like the spin of a planet, but it's kind of the closest analogy. And we use, and when they teach us in physics, they teach to us to use a right hand, and according to, if you go like this, it's going to be up. If it's going like this, it's going to be down, right? And so one particle will have a spin up and the other down, because they need to cancel out, because there is this conservation principle where if you started with 0 spin, the two particles they can have a positive spin and a negative spin, but they need to cancel out, right? Is this how it works, right? How you create this entangled state? Or do you have other way to create?
Yeah, sure. Well, there are many different ways.
Many different ways.
Qubits. Yeah. And in particular, the Willow chip is one of the most popular ways, which are superconducting circuits. So they're just loop circuits that are superconductors. And then you can imagine that the current's going one way or the other way, right? And then you have many of those, and you have to supercool it, which we'll get onto, down to a tiny fraction of 1 degree above absolute zero. And only then can this superposition and entanglement happen in practice. We'll talk about some of the other methods are used.
So in general, though, the two particles, somehow, we don't know, because it's one of the biggest mystery in physics, in nature. We don't know exactly how they know what the other particle is doing, but you can separate them. And the idea is that if you observe one of a state of this particle, there is some kind of a link that is actually, it's not limited by the speed of light, right? It's happening instantaneously. So when you observe something here, something will happen to the other particle. And if this is up, right, if there is one property that is, you are observing it and is supposed to be up, right, you observe it up, you will have to conclude that the other one is actually down. And it happens immediately. It's almost like observing them at the same time, even if you didn't observe the other one. Is this a fair representation of what
sure, I mean,
entanglement means?
You try to get these things entangled. So in the simple case, you can imagine the electrons spin up, spin down, you get them entangled, you separate them, and they remain entangled unless some other influence happens that causes the spin of the other one to flip, right? So they're entangled until they're not. And that's the whole problem, is noise reduction in these quantum computers, because there are lots of things that might disentangle them. So we talked about some of the categories of applications. We're interested in cryptography here. Let's talk a bit about scaling and which technology. So superconducting loops is what Google is using, and IBM and Rigetti and some of the other main ones. But there are other categories. Trapped ions is one. Neutral atoms is another. Photonics. Photonics is interesting because all of these others typically require very, very cold systems just above absolute zero. But photonics you can do at room temperature, whereas they have to get down to millikelvin, so less than 1/1000th of a degree above absolute zero.
And I heard other people trying to explain this thing that we're now physicists, and they say, oh, these are, you need to actually reach zero temperature. You cannot reach zero temperatures. That is one of the property of, because basically that will mean that everything completely freezes, and that is never possible. You can come closer and closer and closer, but you cannot reach zero. It's very close to zero, right? So
it's amazing how close they get. So what they're fighting against is noise and noise and more noise. There's vibration noise, there's thermal noise, there's electromagnetic, external electromagnetic noise, and then there's crosstalk within the system noise as well.
And explain this thing about, I'm sorry, I'm trying to think about, the average audience. Say a couple of words about how physicists understand temperature, right? We have this scale that is a favorite scale. People use Fahrenheit, Celsius, but physicists use Kelvin, right? And the idea is that you can have, in theory, an infinite Kelvin, right? In the upper end, there is not really a limit, but there is a limit in terms of the lowest possible temperature. We call it zero Kelvin, and then it does correspond to a certain number of Celsius or Fahrenheit. So can you maybe elaborate on that? And what that means in terms of
well, just to keep moving, because that is kind of a diversion, but the very simple view of that is when everything stops moving, because temperature is basically goes as the square of the average velocity, in the air and something else, right? It's the average velocity in random directions squared is proportional to the temperature. So you don't want things moving around, right? And that's why you want to get it down to zero. Now, there are other ways, attributes of temperature, but we don't have time to get into those. The other important thing, besides fighting noise, is the temporal coherence. You want this superposition to last for a long, long time. Well, right now, the state of the art is microseconds. That's the best they can do. In fact, Google just, with this announcement, is very proud that they were able to maintain coherence for 100 millionths of a second, 100 microseconds. So, that's much, much less than a wink of an eye, but they had been at 20 microseconds in their prior generation. Then you want to scale the physical qubit count as well, and then you have to keep the coherence spatially, right? Because you have multiple nodes or qubits, and they're built out of physical systems, and they have these distances keep growing, right? As you build a larger and larger machine, or as you put multiple chips together, and they've got to keep that coherence over a longer distance. Then you have the control and measurement problem. And then you have the problem that as you add qubits, typically noise degrades. It gets worse proportionally. And decoherence can get exponentially worse. So this is what they've been fighting for. And we've been in what's called the NISQ, or the noisy intermediate scale quantum error. And on the next slide, this McKinsey roadmap kind of breaks things down in terms of where we are and where they're trying to go. And we're trying to go from early stage, which is noisy and intermediate, and has, order 100 physical qubits. And you want to look at the blue dot, not the black dot. The black dot is for annealing quantum computer design, which is special purpose and cannot be used for the cryptography that would affect Bitcoin. It's used for optimization problems. It's more like an analog machine. So we're in this early stage, and we're starting to get into the late stage where you get to 1,000 physical qubits. But there's not enough fault tolerance now in quantum computing. So they want to get to fault tolerance early stage and 100,000 qubits. And in order to break cryptography, you need to get to that fourth column, the fault tolerant late stage. You need to have of order 1 million or more physical qubits. And that's shown with this, box that has the black fuzzy outline. And then it shows at the bottom breaking RSA cryptography. And you need a high degree of fault tolerance. And then the universal supercomputer quantum, would be beyond that. And look at the logical numbers. Right now, the logical numbers are like 1 or 2 or very few logical qubits. But for fault tolerant late stage to break cryptography, you need of order 1,000 logical qubits. So we're still in the early stage for quantum logic gate-based general purpose, not these annealing machines. And right now, Google has 105 physical, and IBM has 1,100 gate-based qubits from which they can build logic, but they need many, many physical ones per gate because of all these noise problems. Now, here's a comparison between the first microprocessor, the Intel 4004, which came out in 1971, and the Google announcement of their Willow chip in this past week. The Intel had 2,300 transistors and from 500 to 1,000 usable gates. And remember, that's where we want to get to. We want to get to 1,000 usable logic gates for quantum computing. We're nowhere near that. Their clock was quite slow. It was 0.7 megahertz. The Willow chip, you can't make it just out of silicon. You need very exotic superconducting materials like niobium and tantalum and others. They're now at 105 qubits, but from that, they can get 1 or 2 logical qubits at a certain level of noise. And that only can be 1 gate at most. So instead of 1,000 usable gates, 1 gate. And the clock rates are faster. Their gate times are around 10 to 100 nanoseconds. And that's, it's not a precise clock in the same sense, but it's in that range of 10 to 100 megahertz. And here we are, 53 years later. And they have improved their quantum coherency time with this latest release. And they've got improved error suppression over prior generations using what's called a surface code technique. Now, we don't know how fast quantum computing is going to advance. So we can look back and see how fast has it advanced over the past 20 years or even the last 5 years. And then we can make different projections going forward. And this slide is not showing my projections, it's from someone else. But it seems like we've been slower than Moore's law heretofore. IBM had 5 qubits in 2016, now they have 1,100. So they have been faster than Moore's law for the past, 8 years. Google, they had 53 qubits 5 years ago, and it took them 5 years to get to 105. Now there's some other things that got enhanced, but that's slower than Moore's law on the rise of physical qubits. Rigetti is another one of these superconducting loop type designs similar to IBM's and Google's. They went from 8 to 84 in 7 years. So that's around Moore's law. And then you have this 5-front battle where you need to scale up the number of qubits. You need to get more logical qubits from those by suppressing your errors. And right now, the state of the art is maybe you need 1,000 physical qubits to get 1 logical qubit. they would hope to get that ratio down. You need to drive up the clock rate, and then you need coherency to improve for longer lifetimes and also stretching across wider domain and spatially. So the chart shows projections where you're on Moore's law rate, where you double every 2 years. That's the gray line with dots at the bottom. If the number of qubits were to double every year, which would be much faster than Moore's law, then code breaking would reach, it could do the code breaking by about 2040. If they proceed more quickly and can double their qubits every 9 months, then they would reach the ability to do code breaking maybe in the first half or the middle, really, of the 2030s. And right now, I think that's roughly the trend that we may be on. Probably the soonest is 10 years, but we want to be prepared in case there's some massive breakthroughs that make this a problem within 5 years. So what are the problems? 2 categories, addresses and hashing. For addresses, it's called Shor's algorithm. And what you're doing is you're breaking the private key of public-private key pairs. This is used everywhere in finance. This is used everywhere in the defense and national security infrastructure, and widely in industry, not just in Bitcoin. So this is an issue for everybody. Shor's algorithm is exponentially faster for larger numbers than a classical computer would be. Right now, the keys that are used in Bitcoin are elliptical curve digital signature addresses based on a 256-bit private key, which has 10 to the 77 possibilities. Now, Shor's, in its first implementation, was like factoring prime numbers, which is like the old RSA style, but it can be adapted for the elliptic curve logarithmic problem that's relevant here. And that's a generalization of factorizing prime integers. Okay, so Bitcoin addresses in the early days use something called P2KP, and unfortunately, those are all exposed. That is, the public key is exposed, and then if you have a powerful enough quantum computer, you could crack the code and learn what the private key is. So that got improved with a design in 2010 that got rolled out to wallets over time, but mostly was adopted in 2011 by adding a hash feature. And so these keys are not exposed until you actually move the coins. And so when you move the coins, you do have to expose the public key. And so for that duration, a quantum computer could potentially intercept and steal the coins. So that's the whole, addresses issue and the keys issue. And then the second question that comes up is hashing, hashing the blocks on the chain itself. There's a different algorithm. It's a search algorithm called Grover's algorithm. Could you hash blocks? So I'll talk about both of these, but our emphasis is on the first one. This is a nice little chart that's been built by Ben Sigmund. You can follow him at Ben Sig. That shows those two with the digital signatures and the keys in the top row and the hashing in the second one. They both have SHA-256 encoding underneath. The number of logical qubits required is about 2,500 to 3,000, and that means you need millions of physical ones. And that would undermine the transactions themselves and the keys, that you use in your wallets. For hashing, it's similar. You need maybe 1,000, 1,500 logical qubits. And again, you need millions of physical qubits. And what it would do is make quantum computers just potentially faster than the ASICs that we use today. Let's address the first one, the second one first, because it's the easier to dismiss. The quantum search algorithm with Grover's, the fastest it's ever been run is 4 qubits. There was a paper in 2022 that ran 6 qubits on a simulator for the IBM machine. And they made some comment about the IBM machine. Back-end results are not promising. Actual qubits still suffer from lack of coherence. So the largest actual Grover's algorithm that's been run on hardware, 4 qubits. And remember, we need to get above 1,000 in order to even do any sort of, even a single hash. So Grover's for Bitcoin hashing. Typical ASIC is now 200 plus terahashes per second. There are ASICs coming out with as high as 800 terahashes, supposedly by the end of the year. You need 1,000 or more logical qubits, and you would need 1 million of physical to achieve clock rate hashes per second. So if you have a quantum computer with a megahertz clock, 10 to 100 megahertz clock, it would produce that many hashes if it had 1,000 logical qubits. Well, 100 megahertz is nothing compared to the 200 terahertz clocks or 200 terahertz rates, essentially, that we have with 200 plus terahashes. And a hash is not just one operation. There are hundreds of operations involved in a single Bitcoin hash, which you see in the block on the right-hand side. Bitcoin uses double SHA-256, and a single SHA-256 has multiple rounds, and it all adds up to 384 core operations. You have to times 2 that for double SHA-256 calculations. So that's what's going on for every hash of a terahash. So to get there, the clocks would have to be faster by 2 million times. You'd need 1 million qubits instead of 100. That's another factor of 10,000. And if you were to grow at Moore's law rates, you would need 21 doublings on the clock, 13 doublings to get enough qubits, and that's 34 doublings. So if it takes 2 years per doubling, that's another 68 years. And it puts you out into year 2093, and all you do is catch up to today's rates. ASICs are not standing still. If you could do your doubling every year, well, then it would, it would be that much sooner, but you'd still be close to year 2060, and the ASICs get faster and faster. And then on top of that, that would just be one machine trying to challenge one ASIC miner. And we've got millions of machines deployed. And in addition, you have the difficulty adjustment. So there's no reason in principle not to allow quantum computer mining, but they're really not going to be a player in the first half of this century. Okay, so let's move on to Shor's algorithm, the more important of the two. So what you need there is you need quantum safe keys and addresses. And there is now a Bitcoin improvement proposal that would implement those. And it just got a number in the last 24 hours. And the number is 360. So BIP 360. And the author, you can follow the author at Crypto Quick. And, he has a pseudonym. And basically, it's going to integrate if it gets approved. And it's early stages, so it's got to go out for a lot of discussion and review and, decide to where to put the emphasis on. But it implements 4 possible post-quantum cryptographic algorithms. Now, there are standards that exist for these algorithms, and they've been defined by the National Institute of Standards and Technology. So those would be the standards that would be adopted. There's one other. But there's complexity around the implementation. To implement quantum resistant algorithms into Bitcoin increases computational requirements and substantially larger key sizes. Now, the proposal would use a SegWit type of method to put a lot of information in sort of a witness type area so that it would not impact the core of the blockchain as directly, but it still, would drive things up, potentially as large as 10 megabytes or more for block sizes. Now, remember that there were these 2 kinds of coding: addresses that are visible with P2PK and those that are hashed, and only on the fly are they visible. for the public keys. So one of the mitigation activities that people can do is, if you have any early balances pre-2012 and are fortunate enough to have those, then those are the ones, along with Satoshi's coins, for example, and whales in general, that are most at threat. They're going to go after the big balances first, and the easy ones, which would be those. These are the Federal Information Processing Standards. They were adopted as of August this year. And there are three here. There's both keys and digital signatures. There are two types of digital signatures, lattice-based and hash-based. And we don't need to go through the details, but one of them is called Sphinx, and the other one is called dilithium, and those are part of this BIPS 360 that's been proposed. Okay, we're starting to wrap up. Some observations by experts. David Marcus says, there's been a lot of FUD with the Google announcement. When quantum computation hits, the banks, the nation's secrets, will become more vulnerable before Bitcoin. You know, there's a lot more than 2 trillion in value out in the banks that will also be under threat. So it's everybody's interest to get post-quantum cryptography in place. Mara is the largest of the publicly traded Bitcoin miners, and they're quoting physicist Sabine Hossenfelter. Practical applications of quantum computing are about 1 million qubits away and decades from reality. And breaking cryptographic code, the requirement jumps to 13 million qubits or more. They may be able to do it with somewhat less, particularly with this surface code. You know, maybe they can reduce noise more rapidly, but they're so far that we're going to be able to see what happens and how this develops. Ben Sigmund is a good one to follow. Ben Sig, he's been tracking this, so you can follow him. Adam Bach says millions of physical qubits all entangled. We're 5 orders of magnitude away, and at the same rate of progress as the last quarter century, 50 years away. I think that's a very optimistic view. I think, you know, they're probably going to be a clear and present danger sometime in the next decade, but maybe more likely the end of the next decade. And Old Lehman is another good one to follow. Okay, with that, I think we can wrap up. I'm going to show, that's these resources, other resources that you can look at. Scott Aronson blog, he's a quantum physicist. The Ozzy Roddy blog for the details of the Google Willow. I mentioned these next two. Old Lehman says, really what we need are just walls, defenses, doors, and locks. Upgrade.
Yeah, I like that analogy. He was saying something like that. Think about Bitcoin like a castle, and that is strong, but you know, maybe the door once in a while they need to be improved, and it's not a big deal, you know. So my position about this is, and I made a post, is look, it's clear that it's not an imminent danger. It's also clear that it could be a danger. So implementing these changes, maybe step by step or small little testing, if anything, it could make a case, right? I don't like too much the idea, oh, let everybody else figure it out and then Bitcoin will follow. Bitcoin could be a leader, because in fact it could be a test ground to apply some of this strategy. And I know it takes a soft fork, it takes the community to come together, etc. But you know, this could be actually a selling point, you know, for Bitcoin, because let's say that we solve this before everybody else, we could actually say, that is one of the reasons to join the network, that we have this thing that is already safe for these possible attacks. And so I will not wait too long. I know that is a balance between, because you know, Bitcoin is almost perfect as it is, right? So there is no reason to change it unless there is a reason. And this could be a reason where when people say, what is the value? There are a lot of value. We can continue our discussion why Bitcoin has value. You know, we covered some points, but we can go in more depth. But this could be an idea of actually showing leadership in the community, where it's an added value, and we can actually tell people, look, if you really want a safe place where your assets are fine and they are protected by quantum attacks, invest in Bitcoin. It could be one more point in the list of valuable things that Bitcoin brings. Do you agree with that? Do you
Well,
see it in that
absolutely.
way?
Just like the ETFs have opened up a wide channel for fiat to flow into Bitcoin, and Saylor's opened up a wide channel with his financial engineering and business plan for fiat to flow into Bitcoin, and maybe strategic, Bitcoin reserve is another channel. This would be a big channel for people worried about the safety of their money, throughout the banking system, right? We could say, here's another reason why Bitcoin is a safe place to store value that increases over time as a
Right.
power law.
Yeah, exactly. I'm looking at some of these questions. I don't see too much relevant question. I can give a couple of minutes for people to maybe ask something. I know that the presentation was amazing, and you can see it's a real physicist talking about topic that he understands. So it was a really incredible pleasure. I think it is actually one of the best presentation I have seen on quantum computing. Yeah, so maybe some question that I see here about the crash. It's not really a crash; it's a
Not a
correction.
crash.
Yeah, and I will not worry too much right now. There is a little bit of FUD coming up, right? People go from excitement, oh, we are going to 1 million in the next couple of weeks, to, oh, we are going to crash to 80,000, etc. Let's see what is going on. We are supposed to be in a bull run. We didn't go too far to have a correction, so I would say not to worry. But like always, and if there is a correction, it's an opportunity to buy Bitcoin cheap. So I don't see too many questions. I was supposed to make my own presentation, but I want to keep this meeting close to an hour, so they are digestible for people, and we cover a lot of material. So I don't mind to cover it next time. We can come up. I can talk next time about this topic when we meet next Wednesday. So you guys have one more question, maybe related to what Stephen talked about with quantum computers. Otherwise, I say all the time when I don't see questions and I do a presentation, I tell a story of my dad. My mom will come and say, I made all this food and nobody's telling me that it's good, and what is going on. And my father will say, he was like in the military, will say, if the troops don't say anything, that means the food was good, So that is, if people don't have questions or comments, it means that it was a
We
great
know it's
presentation.
complex. It's a lot to absorb. It was difficult for me to put it together. It's a difficult topic. But I think the one takeaway is that people should just track that BIP 360 and see how that develops, because that's right now the best proposal that Bitcoin has.
Great. And if it is good and there are no huge problem, it will be great to implement it. I would say sooner than later, and I don't know. I'm not, a developer. I don't know all the issues and what it takes, etc. But it could be like a sign of leadership of a community and say, see, actually, we are testing it on Bitcoin and we're making Bitcoin safer. And actually, this is one more reason to invest in Bitcoin. So it's an idea. Hopefully, something that maybe is useful to think about. Anyway,
we'll track it and we'll update people.
Yeah, but please don't worry, because like with all the dangers, all the threats, you need to think about solution. There are solutions people are implementing. We have a fantastic community with a lot of very clever people, very prepared people, and before it becomes a real threat, very big countermeasures. So I will not worry. It's not something that I will lose sleep about. Just be informed, learn, because again, we've had fantastic thing with Bitcoin that now a little bit of quantum mechanics that maybe you never thought you will learn in your life. And it's one of the opportunity to learn more things, to go deeper. It's amazing, right? I'm learning about economy. I thought that I will never learn anything about economy. I wanted only to study physics, and now I'm learning about economy, studying books about economy. So we learn a lot of things by being Bitcoiners, you know. So do you have the same experience, Stephen, that you're being exposed to things that
extremely multidisciplinary.
Yeah.
Yeah.
So, okay, we can wrap it up here. Thank you so much, Stephen, for another amazing presentation. Hopefully, this is something useful, and you guys can watch it. You know, you can go back, look at the slide, and contact us. You know, if you have any questions. Both Stephen and I are very active on X, and so you can DM us, right? I don't think it's a problem for people to DM you and ask you questions. So, you know, maybe next episodes, if you can also ask questions from the previous episodes with some people sometimes watch them offline. So, okay, great. I think it was a very interesting episode. Thank you so much, Stephen.
Thank you, everyone, for joining us.
Thank you, everybody.
Until next week.
See you.